Hello and welcome to part 2 of the Year 13 homework. This is question 6. Find a set of values of x for which f dash of x is greater than 0. So this is also the definition of an increasing function. That's another way you can ask this question. You can just say find a range of values of x for which the function is increasing. Well, let's do it. We need to differentiate it, and to differentiate that, we're going to need quotient rule. It's the easiest way to do it if you ask me. Low d high. Right, that gives me that. Minus high d low over the square of what's below. That's a little rhyme anyway, which I use. That gives me 2x squared minus 4x squared, which is minus 2x squared, add 6 over x squared plus 3 squared. And that's what f dash of x equals. Now, we want this to be greater than 0. Now, let's find where it equals 0 first, yeah? We can, actually, no, well, what we can do, if in the equality case, the denominator is just going to be absorbed by the 0. It's going to be times over there, and you're just going to be left with minus 2x squared plus 6 equals 0. So what we can say is, actually, we can use this for an inequality now. As we want f dash of x to be bigger than 0, we want this to be bigger than 0. Same thing's going to happen. We're going to times that over there. Since it's a strictly positive amount, it's not a problem anyway. So 6 minus 2x squared is greater than 0. So 6 is greater than 2x squared. So x squared is less than 3, if you like. Well, if x squared is less than 3, that means x is trapped between minus root 3 and root 3, yeah? Draw the diagram if you're not convinced. Draw the diagram of y equals x squared minus 3, the graph of x squared minus 3. Because if you can imagine this being taken over there, we want that expression to evaluate underneath the x-axis. And as this goes through minus root 3 and root 3, we can see it's a beard and we need minus root 3 to root 3. And that is the end of that one, really. That's all you need to do. Let me just check my answer. Yep, it's all good. So yeah, that one's not too bad. 7's a bit harder because it's got this this famous result. I like using logarithms to prove this result. Let's let y equal 2 to the x. If you don't like using this notation, this d by dx notation without a letter being up there, and sometimes I don't, then use y equals, just say let y equal 2 to the x, yeah? Well then, natural log of y equals natural log of 2 to the x. So natural log of y is x times the natural log of 2. Yeah, and this is the alternative without having to write it with an exponential function in there. I quite like this way of doing it, actually. Now, what we're going to do is we're going to differentiate implicitly. So we're going to do d by dx to both sides of this equation. Now, when you differentiate this, you're going to get 1 over y, but because you differentiated a function of y, you're going to times it a d by dy by dx. And that's simply because d by dx is exactly the same as doing d by dy, in other words, differentiating with respect to y, and then timesing by dy by dx, because they would cancel, giving that. So that's why we do it like that. But all you really need to remember is it a function of y? Stick a dy by dx on the end and differentiate it normally. That's the way I see it. Okay, on this side, it's even more nicer in some ways because ln2 is just a number. It's like 3 or 7 or 15. And when you've got 15x or 3x or 7x, it differentiates to 15 or 3 or 7. This is no different. It's just going to differentiate to the constant it's being multiplied by because ln2 is just a number. You can work it out on your calculator and write it as a, approximate decimal, and you'll see what I mean. Anyway, hence dy by dx is y ln2, but y is 2 to the x, so you get 2 to the x ln 2 just as required. And we've proved it. Okay, the curve C has equation there, and it wants to find the equation of a tangent to C at P. Okay, this looks like quite an ugly one, but we're going to differentiate everything with respect to x. We're going to get 2 plus 6y dy by dx. Plus, okay, here's a really awkward bit because we're going to need product rule for it. If we differentiate this, we get 6x, times it by the other side undifferentiated. We do not need a dy by dx there because we didn't differentiate any functions of y. Now differentiate this side, 1, then you need a dy by dx, but you need to times it by the other side undifferentiated as well. 12 differentiates to 0, and then 4 times 2 to the x, well, think of it as 4 times 2 to the x ln 2. because you already know that 2 to the x differentiates to 2 to the x ln 2, and constants in calculus just kind of hang around. Okay, so what does this give us? This gives us dy by dx, open bracket, 6y plus 3x squared equals 4. I mean, I suppose what you could do to make this look a bit more attractive is move that all the way up to be that power there, yeah, because it doesn't matter which order we're timesing in. So this is 2 to the x ln 16, and then we've got a minus 2 minus 6y. And then we can work out an expression for dy by dx. It's 2 to the x ln 16 minus 2 minus 6y all over 6y plus 3x squared. Okay, we know that the point 2, 0 lies on C, and we want to find the equation of the tangent at 2, 0. So I'm going to plug in those values to find the gradient of the tangent. Okay, the gradient of the tangent here, well, what's it going to be? We're going to have 2 squared, which is 4 ln 16, minus 2 minus 0 over 0 plus 3 times 4. So by the look of it, we're going to have a third ln 16 minus a sixth, which is interesting. Okay, I'm now going to, essentially this is going to have an ugly answer. Now they just want an equation of the tangent. Well, I can just plug it in now. Y equals, or y minus 0 equals a third ln 16 minus a sixth times by x minus 2. Yeah, that's it. I've done it. Notice, because I'm using y minus y1 is m times x minus x1, I can be supremely lazy here. I don't have to find a plus c or anything like that. I've just got my answer straight away, which I'm really happy with. You know, it's just like, right, great, that's it, it's done. Now, I'm just checking it with the mark scheme. They've written it in a slightly different format, but I think it's correct. Yep, it's correct. Cool. I've just, I cancelled down my, because I changed that to ln 16. Looks slightly different to theirs. But yeah, if you've got something equivalent to this, it could easily look equivalent. They will accept inexact answers here as well. So there we go. They do accept inexact answers. But I just thought 4 over 12 is a third ln 16 minus 1/6. Check the exact value. I think it comes to, according to the mark scheme, 0.76x minus 1.52. If yours rounds to that, then I'm sure it's also correct. Okay, next one. What we got here? X is tan squared 4y. Find dy by dx as a function of x. Okay, so the typical way of doing this is to differentiate this with respect to y, sorry. What we got, tan squared 4y. I can't even copy down the question correctly. Right, okay, if we're differentiating this, we need chain rule. Think of it as tan 4y squared. Differentiate inside the brackets. You're going to get then, tan differentiates to sec squared, so it's going to be 4 sec squared 4y. We've differentiated inside the function. Now we'll differentiate stuff squared, and that differentiates to 2 times the stuff. Okay, so to write it a bit clearer, we're going to get 8 sec squared 4y tan 4y. And that's dx by dy. Now, we will need dy by dx as a function of x. So I need to flip it. We're going to have 1 over all of this. Now, that tan 4y is no problem because I can write that as root x. The sec squared 4y is a little bit tougher, isn't it? But as 1 plus tan squared 4y is sec squared 4y, all that matters is those angles are the same. What I can say about the sec squared 4y is it's the same as 1 plus x. So I've got 1 over 8 times 1 plus x times by root x. Let me just quickly check my answer there. Yeah, I think they've written, yeah, it's exactly the same. Cool. Okay, so, sorry, yeah, I forgot this bit. I missed this bit. So I've just got to change the format. So we've got 1 over, let's times that root x in, keep the 8 outside. That's probably right. X to the half plus x to the root 3 over 2. Sorry, 3 over 2, not root 3 over 2. And so, yeah, if you like, let's just write it all in index form. Half plus x to the 3 over 2. So p is a half, q is 3 over 2, if you like. And a is 8. That's it. It's done. Okay, right. Part 2. The volume V of a cube is increasing. I quite like these questions, actually, these rates of change questions. You may feel completely differently, but I quite like them. I think they're quite good fun. I'm just moving it over so I can see what I'm doing, get away from some of the working I've already done. Okay, the volume V of n cube is increasing at a rate of 2 centimeters cubed per second. Those units tell me that that must be dV by dt, because it's volume divided by time. So dV by dt equals 2. Find the rate at which the length of the egg of the cube is increasing. So we're looking for, if we call our cube side length x, we're looking for dx by dt. Yeah, this is side length x. We need dx by dt. Yeah, and the volume of the cube is 64, so we know V is 64. Okay, cool. So we've got some interesting stuff. We're looking for dx by dt. We've got dv by dt. I put it like this. I want dx by dt. I've got dv by dt. What do I have to times this by to make that? Well, I need a dx on the top, so I need a dv there on the bottom, and then it's going to work. Now, it means I need dx by dv. Now, there's a really easy connection between x and v here, because x cubed is v, because that's how you work out the volume of a cube. So dv by dx is 3x squared. And so now I can say dx by dv is 1 over 3x squared. So dx by dt is going to be the volume, the rate of volume change with respect to time, which is 2, and then 1 over 3x squared. Yeah. But if the volume of the cube is 64, then x must equal 4. Yeah. Because when the volume is 64, x equals 4. So I can plug that in now, and I can just say this is 2 times 1 over 3 times 16. So if I look at that, that is going to be 1 over 24, I believe, centimeters per second. And I've got it right. I've just looked on my other screen, and that seems to be correct. Okay, let's just do the two proofs to finish things off. Okay, proof by contradiction. Right, if you start a proof by contradiction, always start with this word or kiss goodbye to 1 mark. Assume that there are positive integers, that there are a pair of positive integers P and Q such that 9p squared minus q squared equals 49. So we've basically assumed that this is soluble in integers, which we're then going to show if we assume that we arrive at a contradiction. Now, a standard way of doing ones like this, difference of two squares, 3p plus q, 3p minus q, is 49. Now, we wouldn't normally factorize it when it doesn't equal 0 on this side, but the one exception I'll let you do that for is if you know that this is a whole number and these need to be whole numbers, because then we can do a prime factor decomposition on the 49. Because when you do a prime factor decomposition on the 49, you realize there's only two ways of making 49 by timesing two numbers together, and that is 1 and 49. 1 times 49 is 49, or 7 and 7. 7 times 7 is 7. Now, let's consider two possibilities exist. Notice in my proof, I always write down sentences. Yeah, full sentences. You have to. I don't like doing it either, but you have to. Okay, either 3p plus q equals 7 and 3p minus q equals 7. It's pretty obvious there that q must equal 0, but let's add them together. We get 6p is 14, and that means that p is 14 over 6, which is 7 over 3. But that breaks my assumption that p and q are integers. But this contradicts our original assumption. Sorry about the handwriting here, it's getting worse, isn't it? Our original assumption. Okay, so maybe it's the other possibility that exists. The other possibility is that one of them, and let's assume it's the smallest one, is 1, and 3p plus q, the other one, must be the 49. Add them together, you're going to get 6p is 50, but that means p is 50 over 6, which is 25 over 3, which is not a member of the integers, yeah? So this contradicts our original assumption again. This also contradicts our assumption. That doesn't make any sense either, does it? So what we've proved is, you know, if this is in fact true, you're bound to get values of p and q which are not integers. Hence, I can now say it is not possible to find two values p and q, or there are no positive integers. Let's just write exactly as I put it. Hence, there are no positive integers P and Q such that nine p squared minus q squared equals 49. Yeah, there we go. And that's a full proof by contradiction. And then I've got a little bit of a, one of these disproof questions, counter examples. They're dead easy, really. I mean, John claims that if n is a positive integer, n squared plus 11n plus 11 is always prime. It's false. It's false. We don't know any formulas for prime numbers. We know some, like, which put upper bounds on prime numbers, and we know some about the density of the primes, but a formula which always generates a prime number, maybe a Mersenne prime, I don't know, but anyway, this has a very obvious value of n, which you can pick for its false. How about n is 11? Because if you choose n is 11, you're going to get a multiple of 11 plus a multiple of 11 plus 11. Yeah. Now that gives you 11 11s plus another 11 11s. That makes 22 11s plus another 11. That is 23 times 11, which is clearly not prime. Which is clearly the opposite of prime, by the way, is composite. Hence, John's claim is false. All you need to do to disprove something is find a counterexample. And that's it. That's a dead easy one. That one, that's not too bad at all. Okay, so hopefully that was useful. Keep up the good work. If you want to know where I got all these questions from, they're just actually from the old C34 past papers, which was like an international A level. But if you look at the C34s, just Google C34 past papers, you'll see what I mean. It's got all of this topic, all of this stuff in there. I hope it was useful anyway. Sorry if I sound a bit tired. I'm feeling a bit tired. But yeah, hope it was useful. And yeah, keep up the good work and let me know if you're stuck. All the best. Best of luck in the test. Bye bye.